Okay, so last time we discussed the structural risk minimization, the structural risk minimization approach. And the structural risk minimization was an approach that's saying kind of a guideline for how to design an algorithm. Rather than doing ERM that says the algorithm has to find the element of H that makes the minimum error over the sample, now we are introducing a new component, and we say it's not only that you want something that will be accurate as possible, but also you want it to be as simple as possible. So we have this notion, we introduce this notion of weight, and we have this, so introduce a notion of weight, and we have some accuracy complexity trade-off. That's what this kind of approach suggests. And to remind you what exactly is this, or one manifestation of this accuracy complexity trade-off, let us go back to the example of minimum description length. So one example of structural risk minimization is the minimum description length, learning, the MDL. And we said that the MDL learning consists of first picking. So the first step, I'll call it zero step. It's before you see any examples, is pick a description language for your H. And a description language, we just mean a way to describe every element of H, every function. It could be a code of a program that computes H, but it could be anything else. So we have to pick a description language, and the only requirement that we had for a description language is that the description of every H is a binary string, and those binary string, this set of binary string, is prefix free. We don't want one description to be an initial segment of another description. So you pick a description language for H, and then when you see the data, and now upon seeing the training sample S, we do step 1, which is pick H in H that belongs to arg min. And now we want to minimize a sum of two components. One of them is ls of H, and the other component is the component that has to do with the description length. So here we have the description length of H plus ln 2 over delta divided by 2m. So now the rule is that when you see the data, you're trying to minimize a sum of two terms. The first term is the accuracy term. You want to make as few as possible errors on the sample. But the second term is the more interesting one, is the complexity term. You penalize for H's with long description. And here we kind of long description, we interpret this as equivalent to being complex. So you're trying to pick an H that on one hand will fit the data well, but you also want to save on the penalty in terms of the complexity of H, or the length of the description of H. Right? So we saw that this was just one manifestation of this more general structural risk minimization. Structural risk minimization can work with any weight function W. And here we chose a weight function which was particular, and the weight function had to do with the length of the description of H. The weight function that we chose here was W of H equals 1 over 2 to the description length of H. So with this choice of weight function, we got this rule. Structural risk minimization can pick different notions of weight. Okay, well, there was a question here?
I don't think it's very important. Like, last time we put it on the board, we didn't have a 2m factor. It was just m on the bottom, but it doesn't matter.
Oh, yeah, maybe. You see, what she's saying is that she thinks that last time I didn't have this 2 factor here. I'm not very good at constants, so I mean, just check it in the book. But if I think the constant should be there, so it must have been a mistake on my behalf if I didn't put it last time. Any other questions? Okay, so let me discuss a little bit what we have here. There are several aspects that are worth mentioning. So the first aspect, so that we already mentioned, so we want to discuss this, what can we learn from this rule. So the first aspect was, we already discussed it last time, was the Occam razor principle, that the Occam razor principle says that when you have to choose between different explanations, choose the simplest explanation. Of course, it doesn't define precisely what is simple, but here we get a very precise formal manifestation of this rule. Simple means has short description, and it also gives you exactly a formula for trading the accuracy for this goal of having a short description. So that's the first thing. I mean, we have here a formal manifestation of kind of a philosophical principle. Another point which is very important here to understand is the issue of how can we choose, how should one choose the description language. And practically that's a very important problem. If I want to use such a rule for learning, I really have to pick my language. The first thing that may come as a surprise, and it's worthwhile making it explicit, is that this rule will work regardless of what description language I picked. In some way, it is almost paradoxical. It doesn't matter which description language I pick, but once I pick the language, I want to find a short description. Because this short description of H is not something that objectively defined. I mean, I can have a function which is very, very complex, but in my description, I will just encode it as something very simple. I will take this function. I'll take a function, say, that behaves like this. I don't know what, something which is a function, and call this function H0. And how many bits do I need to describe H0? I don't know. To say H, I maybe need some, I have 26 letters in the alphabet. I picked H, so I need something like 5 bits in order to say H. So I have 5 bits to describe this guy. And we do it, and the scheme will still work, no matter what description I picked. There's nothing objective about what is complex and what is not complex. And this is kind of very surprising. The main point is that you have to pick this description before you see the sample. And so every h, which can be either complex or not complex, depending on the function that we picked. Now, why is it not such a paradox? How could it be that some h, I could have here a big penalty in terms of how much error it may incur, and for the same h, I will have a small penalty if I picked a different language? How can it be that by picking a different language, I'm paying different penalty? So we should think of it as in terms of the two extremes. One extreme is that if we fix h before seeing s, we can just fix h. Pick any h and say, this is my h, right? Then we know that L, the true error of h, will be always ls of h plus, I fixed h in advance, so I can think of it as I have here a class with only one guy here. It has VC dimension 0. So what will I will get here something like log 1 over delta divided by m or 2m. So you see, I'm paying here a very low complexity term. I'm paying here as if the description of h has length 0. But the problem is, why is it not a good rule for learning? Yes?
Because the loss always...
This may be very big, maybe very high. If I pick my h in advance, and now I see the data, this may be very high. So we can think of it as measuring how much prior knowledge I have. If I already have a good prior knowledge, and I can pick an h that it will turn out to have low error, then I'm paying very little here. But if I didn't have much prior knowledge, and I just pick an arbitrary h, sure, this term will be very small. This term will be as if the description is 0. But then, because I didn't have good prior knowledge, I'm paying a lot here. So this kind of gives me a trade-off. I can put my prior knowledge by saying those h's are more likely to succeed. I will do well if the h's that I described succinctly also happen to have small empirical error. Then I will be doing well. I'll be doing badly if I misestimated the phenomena, and the h's that are doing well here, I gave them a very big description. So it is the choice of the language is really a manifestation of a prior knowledge. One extreme is that I put all the weight on one h. I only have one h. Everything else, description is infinity. Then I'm really dependent on how well I guessed a good h. Another extreme is pick some finite h. So finite h is, say, some h1 up to some hn. And the description language will be hi. The description of it will be the bits of I. 0, 1, 0, and so on. I in binary. I will write I in binary. So what will I get now suddenly? What will be the description lengths that I will get for every h? Now, for every h in h, what is going to be the description length of h? How many bits in binary I need to describe a number between 1 and n? Yes. Log n, right. Right? And the bound that I have there will get me LP of h is at most LS of h plus, for all h's, it will be the same description, log n plus log 2 over delta divided by 2m, because for every h, this will be for every h in h, because all of them have the same description. All of them have the same description length, which is a log n length string of zeros and ones. So all of them have the same description. This term here, the description of h, will always be log n. Does this formula look familiar to you? What should it remind us of?
The fundamental theorem.
Right, the basic theorem of, you see, if log n, I can replace it by, it's the same thing as saying log the size of h. Right? N is the size of h. With log the size of h, that's the kind of the usual thing that we always had. This is always less than the VC dimension of h. Right? We know that the VC dimension is always, this is the other way. This is always above the VC dimension of h. VC dimension is always bounded by log the size. So if I don't have any prior knowledge, if all my prior knowledge is some finite h, then I can say the description will always be log h, and I'm getting back to my old formula. I have here the size of h. That was our formula for learning a finite h. The first thing we did when we started analyzing PAC learnability, we talked about finite h. We got exactly this formula with here log h. So if I can pick a finite h and say I'm committing to one of the h's here, but I don't care which one, they all get the same description, it reduces back to our first bound for finite h. The other extreme, so here I didn't care about which one of the h's it was. I just restricted myself to a finite h. The bigger the h is, the more I'm paying here in penalty, but the better chance that I can find here someone with small error. That's one extreme. The other extreme is I have a lot of knowledge, I put everything on one h. So I'm putting a lot of risk here, and I'm paying little here. So this is kind of a joint generalization of both learning a finite h and just hypothesis testing. I pick an h and I test it. So picking the language is like picking a class. It's kind of putting in our prior knowledge. And if the class is finite, then we can immediately, from this result, get our old result for learning finite h. Another interesting way of picking h, and this is what is happening. I don't know if you heard the term. I will talk about it in some point later in the course. Bayesian learning. So Bayesian learning is a different approach to learning that I haven't discussed so far, and it's not the focus of this course, but it's worth just mentioning it. And in Bayesian learning, we start with some kind of prior belief on which h's are likely and which h's are not likely. So we start the learning. By start, I mean before we see the sample, by having a prior distribution, probability distribution over the class H of hypothesis. So I have, for every H, I have a probability of H. P of H is how likely I believe that H is the best hypothesis. So in Bayesian learning, I kind of start with a prior belief, which tells me how likely I think each hypothesis is going to be. But now I can immediately translate it to our terms. Because if P is a probability over H, we know that the sum of P of H over all H's in H, what is it going to be? If P is a probability of H, what is the sum going to be? The sum is going to be 1. So we can use this probability as a weight. So therefore, we can use P of H as a weight function. And this kind of rule translates into the learning rule. Structural risk minimization becomes pick H that minimizes. And here we will have the empirical loss of H plus the same square root. But what I will have here is the log of 1 over P of H plus log 2 over delta divided by 2m. This is our structural risk minimization rule with W here. W became the probability of H. So we can also think of it as description length. I'm describing if H is highly likely, will it get a short or a long description? If it's highly likely, it will get a short description. Because if it's highly likely, then this number is going to be big. So 1 over this number is going to be small. And log of 1 of this number is kind of the description. This is exactly plays the role of the description of H. Yes?
I know this is a nitpick, but the second log is still the natural log, ln.
Yeah, I really, it's all up to a constant, and I really kind of consistently confused, if you can say something like this, log and ln, because I don't really care about this constant factor. Yeah. Yeah, it should be ln. Yeah, you're right. Because we get it from taking the log of e to the power. We have the Hofding inequality, and we have the probability of error is e to the minus m epsilon square, and then we take the log of this, and that's where this is our delta, and this is where the log it comes from, and it's ln because we want to get rid of the e. So it's ln. Okay, so you can count it as a point. Yeah. Okay, so what I'm saying is that we have this general principle of structural risk minimization. It works with any weight function. Any weight function that sums up to 1 over all my elements of my big class H. One manifestation is description length. Description length sums up to 1 once it's prefix free. And then we get this rule. Another manifestation is if I have prior probability over which H's are likely or not. Then I get this rule there. In both cases, I really rely on prior knowledge. I will be successful. I will get small error if initially I gave high probability to an H that after seeing the sample, it turned out that it has small error. If my beliefs were not aligned with the reality, then whenever someone has a small error, I gave it a low probability and I'm paying a lot here. Or whenever I gave someone a high probability, it's making a lot of error here. So I kind of try to have some kind of prior knowledge about the world. Not having any prior knowledge is like giving every hypothesis the same weight. Having a lot of prior knowledge, I kind of gamble on one hypothesis. In between, I can give each of them some kind of probability, and I'll do well if I gambled right, if my initial probability gave high weight to those that are likely to have small sample error. Yes?
And for the Bayesian prior distribution, is that a uniform distribution?
No, if it was uniform, then all the H's would have had the same weight.
So isn't it possible to have an H, I guess it's just less likely that an H has a really low probability for smaller sets of functions?
Maybe, let me
Oh, yes.
no, let me explain. It's a good point. What is a good prior probability, right? The problem is, if H is finite, let me just talk a little bit more about this probability. So the question of how do we pick a description length translates into the question, how should one pick a good prior probability? Over H. And one way that people that do this kind of Bayesian learning, trying to say, if you don't know anything about the problem, what should you do? Pick a uniform probability. Don't give preference to any H. So if you don't know any better, use uniform probability. Everyone gets the same. The problem is this works well on a finite H. If H is finite, if H has size n, then we'll say P of H equals 1 over n for each H in H. Right? And that gives us the rule that we have here. But what if H is infinite? If H is infinite, we have a problem. Because assume H is H0, H1, H2, Hn for every n. Then there is no uniform probability over H. Why not? Because if I give everybody 0, they'll be very uniform, but they do not sum up to 1. It will sum up to 0. But if I give everybody else anything else, the smallest epsilon in the world, I'll give everybody epsilon, 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 what will it sum up to? Infinity. It will not sum up to 1. So there is no uniform distribution over an infinite countable set. So I am forced to prefer, to give priority to some H's over others. Because if I want to be completely egalitarian, then I'm either giving everybody 0 and I have nothing in my hand, just 0 probability, or I give everybody some epsilon, but then it's not a probability, it sums up to infinity. So I really need to pick some function. So I can pick many functions. I can pick P of Hn. I can pick it to be something proportional to 1 over n squared. We know that this converges. I can pick P of Hn to be something proportional to 1 over 2 to the n. I can pick many choices. I can pick something that doesn't decrease with n. But I need to make some non-uniform choice, because there is no uniform solution of an infinite H. So when I make this choice, I would rather take into account what I believe is going to succeed on the sample, because that's what will play crucially when I'm trying to estimate my error at the end. OK, so this structural risk minimization is a very general principle. It's the principle of trading accuracy for complexity. Complexity is not an objective notion. Complexity has to do with what we inserted into the mechanism before we saw the sample. And it could be either description length, it could be a probability, it could be many other things. And the best way is to apply prior knowledge when choosing it. And there is no way to kind of overcome it and say I'll be uniform. if the class is infinite. Okay, the last comment I want to make is the question of, can we learn by this non-uniform learnability any h? And the main point here is that we can learn any countable h. What does it mean that h is countable? Countable means that h can be described as h1, h2, h3, hn, and so on. I can learn it because I can describe it, give it a description that will be, or a probability, like the probabilities that I have here. But there are sets which are not countable. So there are, however, there are uncountable classes. Uncountable classes are classes that are infinite, but their size is a big infinity, not a small infinity. Countable is the smallest infinity. And there are bigger infinities, uncountable infinities. Can you give me an example of a class which is uncountable? Yes?
The set of real numbers.
The set of real numbers, but I want it as a class. So I can translate the set of real numbers into a class. So for example, h threshold is an infinite class because it's the set of all hr such that r is a real number. hr is the function that gives 1 to everything below r and 0 to everything above r. How many such h's do I have? As many as there are real numbers. How many real numbers there are? Uncountably many, a big infinity. Is this class learnable? The threshold function, is it learnable or not? Yes. Why is it learnable? It has VC dimension 1. So, sure, there are uncountable classes that are learnable if they have small VC dimension. But there are uncountable classes that cannot even be represented as a union of countably many finite classes. Now, this is something that I promised here, that how many of you are familiar with this distinction between countable and uncountable? So, yeah, I feel that this is not always fully covered in the syllabus of what we are studying here, and it's really a fascinating and fun topic. But it's not very much machine learning. So my compromise on this is that I'll be happy to give a special lecture outside the class hours, outside the exam, just for general knowledge about countable versus uncountable different sizes of infinity. So yeah, this is voluntary. I mean, you can decide whether you want to come or not. It is not part of the material, but so there will be a special lecture, 1 hour, on different sizes of infinity. And I'll try to have it Wednesday next week, Wednesday afternoon next week, which is, I think, March 11, I think.
Yes.
But I will have to announce the class and time when I have to book a room. So I'll announce the class and time and next time in class or on Piazza. But this is just not part of the material. Just to make sure that whoever cares about it has a clear understanding of these different sizes of infinity. Okay. So this is as far as I want to discuss the notion of structural risk minimization and non-uniform learnability. Before we move on to our next topic, I want to mention one other possible version of defining learnability. So I want to talk a little bit about different notions of H is learnable. And I don't want to discuss now the issue of agnostic versus non-agnostic, but the question of what do we allow, what can the required sample size depend on. So in the pack, or agnostic pack sense, we know that we want MH to be just a function of epsilon and delta. We want that if you tell me what accuracy you need and how confident you should be, I could tell you how many examples you require. Then we have the next one was non-uniform learnability. And then we allowed MH to be a function of epsilon, delta, and H. And here I allowed more flexibility, which was I allow the required sample size not only to depend on how accurate you wish to be, but also on which element of H you want to compete against. This is for competing uniformly against all members of H. This says this should work for all H in H and every probability distribution. So here, the for all H in H is not uniform over all the H's. For each H, I allow myself a different sample size. But if we look at it this way, there is also a further relaxation that we can allow. We can allow MH to also depend on the probability distribution. Maybe for each, there's going to be hard probability distributions on which I will allow more samples and easy ones on which I will allow less samples. So this is called consistent learning. Consistent learning, and it is even a weaker notion. Now, this weaker notion, I just allow the sample size, the required sample size, to also depend on P. The problem is, and the reason I'm not discussing it much further, is that I don't know P. In our learning scenarios, we don't know what is the probability distribution. If we knew the probability distribution, we could do everything. We could have come up with the best predictor, the base predictor. So it depends on something that we don't know. So all that it gives us is some kind of guarantee that no matter what the distribution is, if you see sufficiently many samples, if I give you more samples, more samples, more samples, eventually you will have more samples than this bound, and you will have this epsilon delta guarantee. But it will only happen eventually. You can't tell me how many samples I need because you don't know P. But consistent learning is something that is commonly discussed in statistics. A consistent estimator, when you talk in statistics about consistent estimator, is an estimator that as the sample sizes go to infinity, it becomes arbitrarily accurate. But it doesn't give you a bound on how many samples you need in any specific situation. So the notion of consistency is well entrenched in statistics, but it doesn't give you any finite guarantee. It doesn't tell you, because to get the finite guarantee, you need to know P. And as a part of the next assignment that is coming very soon, we will see that in some sense, once you allow consistency, we no longer need to learn. So that will be in the assignment. It will be an exercise that the basic algorithm memorize the algorithm memorize is a consistent learner over any countable x. So if your domain is countable, what is memorize? Memorize just saying you collect all the examples that you have seen so far. When you get a new example, if you haven't seen it before, just guess randomly, flip a coin, or just say 0. If you have seen this example before, what should you do? If you have seen it already in your training data, what will you do? Yes?
Just use whatever the optimized from the training data.
Yeah. Why did I ask you? And it's not as simple as that. I could say, if you have seen it before, use the label that you have seen before. But maybe I've seen it before several times with different labels. So what will you do then? Yes?
Use whatever one has come up most often.
Yeah, use majority. So it just says, if you get you have some sample S, so you have, what is my algorithm upon S when it sees X? What does it do? If X does not belong to the domain of S, you haven't seen it before, predict 0. Doesn't matter. Otherwise, predict the majority label of X in your training sample. Whichever label occurred most often in your training sample, that's what you will predict. Yes? What? What? Yes, X not. Thank you. If it's not in the domain of S, of course. If it's not in the domain of S, predict 0. If it is, do the majority. Right. So that's the memorize algorithm. In the assignment, you will be asked to show that it's a consistent learner. That given sufficiently many examples, it will always be very good. But I don't consider this as learning. Memorization is not really learning. And I don't really consider this as an interesting definition of what learnability is. Well, this one is definitely not only interesting, but really being used in practice. OK? So this is as far as different notions of learnability are concerned. This is the one that we did most of the theory about. This is the one that's most being often used in practice. But the theory of this one was followed from the theory of pack learning. So this is as far as I'm discussing these notions of learnability. And I want to switch to a completely different topic, unless there are more questions here. OK. So the next topic I want to discuss, it's a very crucial thing, and it's the computational complexity of learning. So what do I mean by the computational complexity of learning? When we want to learn, we use two types of resources. One of them is we need training data. And so far, we just analyzed how much training data you need in order to learn. But if you want to implement learning in practice, another very important component is how much computation you need to do once you have sufficiently many training examples. And this becomes really the bottleneck of most learning applications. So it turns out that although we understand so well, we can characterize it with this dimension and all kind of things, how many samples you need, there are two resources. It's the Time we call it the information resource, and this is the training sample size. And the other one is computation resource. And this is how long will our algorithm run once it has sufficient information. And that's a very crucial resource. So I want to turn our attention to this aspect, which is more computer scientist aspect and less statistical aspect. I will not get into a completely precise definition because it really has to do with a course in computational complexity. So I'll only discuss it very, I will discuss in detail the computational complexity of learning, but the definition of computational complexity I will only describe in high-level terms. So what do we mean by the definition of computational complexity? What you really want is to know how much time my algorithm will run. So I have a learner, I have an algorithm that takes emails with labeled spam and not spam and trying to come up with a spam detector. And I want to know how long will the algorithm run before it can give me the spam detector program. And maybe in spam detection I don't care about it so much, but as we've talked before, we mentioned before, there are applications in which this training time is crucial. If I want an algorithm that will predict what should I buy or not buy in the stock market, it'll be useless if it takes a week to compute. What should I buy tomorrow, right? So it becomes a crucial computation. So what we really aim is the runtime of my algorithm. This is what I really want to capture. But the runtime of my algorithm also depends on things like how fast is my processor and how much malware I have on my computer that slows it down, and how efficient was my programming language, and all kinds of considerations which are completely outside the scope of what we want to talk about here. So we only talk about asymptotic behavior, and we count computation steps rather than time. So I don't turn a stopwatch and start to see how much time my algorithm runs. I'm not interested in someone tells me my program ran for 2.376 seconds. What I care about is how many operations did you carry out, steps or operations, and we have to decide what those steps are. And what we will usually allow is we will allow algebraic operations over real numbers. So as a step, I will allow any algebraic operation over real numbers. So it could be addition, multiplication, square root. For us, it will all be one step. So for a step for us will be just algebraic operation over real numbers. That will be a step. We don't care how much time it takes to implement such a step. And we only look at asymptotic behavior because by looking at asymptotic behavior, this O of n notation that you must have seen in all kind of courses, it allows us to kind of sweep under the rug issues of what is my hardware, what is my programming language. All of those are up to a polynomial, up to constants or up to some polynomials swallowed in this O notation. The So this is all belongs to the discussion that you should have seen in other courses, like data structures, algorithms, and so on. What is special to machine learning? There is a big difference that we have to be aware of when we try to use this kind of approach to machine learning. If I have a computational task, so what is the computational complexity? How should we define the computational complexity of learning? It turns out that it's not exactly the same as the computational complexity of doing any other operation. So if I want to discuss the computational complexity of saying sorting, so you get, when I want to discuss algorithmic tasks for algorithmic combinatorial tasks, say I want to find the shortest path between on a graph. So I give you a graph, you have 2 points, S and T, and you want to find the shortest path. Or say you want to do sorting. You have a list of numbers, you want to sort them by order. Then in all those cases, when we talk about this O of n notation, what is the n? If I'm talking about the computational complexity of finding shorter paths in a graph, what is the n when I'm talking about polynomial exponential? Yes? The size of the input. N is the size of the input. What we measure here is the input size. And in this task, the input size is well defined. If I want to find shortest path, it's the size of the graph. If I want to do sorting, it's the size of the list that I want to sort. If I want to do a composition of a number to prime factors, it's the size of my input number. But it's not so clear what is the input for learning. What is an appropriate notion, the parameter that will replace the input size for learning? So what should play the role of the input size parameter in learning? Any suggestions? What is my input when I'm learning?
Sample.
Yes, so one possible answer. So answer 1, it will be the sample size, right? But it turns out when we think about it a little bit more that this is not a good answer. Why is it not a good answer? Because when I want to learn something, if I'll ask for bigger sample, if I use it as my parameter that determines how complex is my learning, I will realize that if I ask for a bigger sample, I can compute for more time. Because if I allow you computation which is O of sample size, then you can cheat. You can have a very complex algorithm, and your complex algorithm needs, say, 1 billion steps. And my sample size that I initially started with was just 10, and it's really a big factor to go from 10 to 1 billion. But you can say, oh, just a second. Give me more samples. Give me more samples. Now when my sample size will be of size billion, suddenly this runtime is just exactly constant. It's just my input size. You see what the problem is? The problem is that by increasing the input, I'm not changing the problem. If here in graphs, if we're sorting, I increase the input, sure, the problem becomes more difficult. But for learning, if I give you more sample, the problem doesn't become more difficult. On the contrary, sometimes you get more samples, the problem becomes more easy. Yes?
What about the size of the hypothesis class?
So one thing could be the size of the hypothesis class, but in many cases, our hypothesis class is infinite. I want to learn threshold function. I want to learn rectangles. I want to go learn a half space. So I cannot take here the size of the hypothesis class. So the problem here allows cheating. But more generally, the input is not part of my problem. So what we will usually do, answer 2, and that's what we will use, is that we will look at learning as a function of epsilon and delta. What really determines your learning is you want to know how much computation I need in order to get accuracy epsilon with probability delta. Of course, the smaller epsilon and delta, I will need more time. So I will really want to have running time that is polynomial in 1 over epsilon and 1 over delta. That is what I would like to have. Usually, we also add here another parameter, which kind of quantifies the hypothesis complexity. Because if I want to output a more complex hypothesis, I will need more time. So this could be like the degree of the polynomial that I'm learning with, or the number of variables when I output a half-space classifier, and so on. So what we will look at, we will say that a problem can be learned in polynomial time if we have an algorithm that runs in time 1 over epsilon, 1 over delta, and some parameter of the complexity of the hypothesis. I will make one more comment about this, and then we will move to examples rather than discussing this notion in abstract. Because the examples somehow are more illustrative than giving a precise definition. So let me just make one more comment. One more issue to take care of or caution about. And this is that we can still cheat. Because now here we discussed what is the input. And we said the input for learning is not a sample size. The input for learning is the accuracy you want to achieve. But what is the output? What is the output of a learning algorithm? What is the output of a learning algorithm? Yes? It's another function. And now the output is a function. It's a function h that goes from x to, say, my labels, right? But now when I want to output a function, it is crucial how I describe the function. Because here is a simple algorithm that can solve every learning problem in very fast time. How will I describe the function? The output of my learner, you give me some sample S, that's my input. My input, you will give me some learning sample S and epsilon and delta. My output will be this description of the outcome. Use ERM on S. This describes my output function. But I ship all the computation to the one that wants to use my output. I gave you an output. It's well defined. But I shipped all the computation to the one that wants to use this output. You see what the problem is? I gave you a good output. I know that it's a good output. But you cannot use it. Now all the weight of computation was outsourced to the one that got my answer. And you asked me, find me a good hypothesis, and I said, sure. pay me, I'll find you a good hypothesis, I take your money and tell you the good hypothesis is this one. Now it's your problem to go figure out what it means. You see, so we want to avoid such cheating. So we also require that in this time, my algorithm not only output a hypothesis, but it output a hypothesis that for every x, so I will define as the runtime of a learner, the runtime of a learning algorithm L will be defined as the maximum between two things. The time it takes L to output some H, and the time it takes that H to output a label on any given x. I don't allow you to give me an H such that all the computation time will be now to take H and try to predict it on a certain x. We have to make sure that what we output can be efficiently used. Okay, so that's, I mean, it's not a formal definition, but this is the flavor of what we have to take care of in a definition. So we only care about, when we talk about computational complexity, we want to focus on algorithms that give you hypotheses which are useful, not hypotheses on which you are going to spend now too much time implementing the hypothesis. So let me, yes?
What does computational complexity mean in the N for uncertainty? What does it mean?
Oh, you mean what is the N here?
Yeah.
Yeah, it's the hypothesis complexity in the sense of what we saw in the non-uniform learnability. It's a parameter. It could be the description size of H. It could be the number of variables in H. It could be the degree of the polynomial. If H is a polynomial, it could be the degree of the polynomial. So this will differ for any task. I can tell you, I am giving you an algorithm that learns polynomials in times which is polynomial in 1 over epsilon, 1 over delta, and the degree of the output polynomial. Or I give you an algorithm that learns half spaces in time which is polynomial in these parameters and the dimension of the half space. So this is a parameter that the user should specify. What do I care about? I will show you an example in a second. So let us, as a first example, consider the problem of learning rectangles. So first examples of the computational complexity of some specific concrete tasks. And I will start with an example. As we go on and see more examples, we will kind of define what we are doing more and more clearly. So my first example, example 1, is learning rectangles, axis aligned. Rectangles in some RD. So if I want to learn axis rectangles, let me, first of all, we want to know what will be my learning time as a function of epsilon and delta. And how will I do the learning? So let us consider the complexity of ERM learning. So assume that my algorithm is just trying to implement ERM for this class. So the first thing I need to know is if I want to output a hypothesis that achieves some epsilon delta goal, what should be the sample size? So what should be, how much sample will my algorithm need to process? Right? So what is the needed sample size? What is mh of epsilon delta for learning where h is, let's call it HD, learning rectangles in RD? Do you remember what was the VC dimension? Everybody remembers what was the VC dimension of axis-aligned rectangles in RD? It was 2D, because in any dimension, we needed to pick a point which is rightmost and leftmost, or top and bottom in every dimension. And once we pick those points, we determine a rectangle. So that was, so the dimension, the VC dimension of HD is 2D. So the sample size is going to be roughly, the sample size that we need is roughly, it has to do with the VC dimension. So it's going to be 2D, which is the VC dimension, plus ln 2 over delta divided by epsilon square, and there was some constant here. That was the fundamental theorem. You take the VC dimension, and it's agnostic, then it's divided by epsilon square. So this is going to be the sample size. This is the minimum sample size that will suffice. Now I have such sample in my hand. How much computation do I need? So I have a sample of this size. So here is my algorithm. My algorithm behaves like this. Step 0, pick, and mh epsilon delta size sample S. Now step 1, I want to implement ERM over this sample. And I want to know how much time is this going to take me. How much time do I need in order to find the best rectangle for such a size of a sample, for a sample of size S in RD? So let me show you a way. One way of doing it is to know the following. How do I go over all possible axis-aligned rectangles? How many axis-aligned rectangles are there? Infinitely many. So how do I go over all of them and find the best one? So the point is that to note that if I have points which are labeled plus and minus, this is my M, and I want to determine any rectangle, I can always shift the sides of the rectangle such that they rest on sample point in my sample. Because if I don't have any point between these two, it doesn't matter where the boundary here will be. So it's sufficient to consider rectangles that are resting on points of the sample. So it suffices to consider rectangles that have points of S on every boundary edge. And now how many such do I have? So the point is that if I'm in dimension 2, every such rectangle is determined by 4 points. If I am in dimension D, every such rectangle is determined by at most 2D points from S. And now I can go count how many such 2D tuples do I have. So if my sample size is M, there are at most M to the 2D such tuples. Are you with me? Is it clear until now? I say, I got my sample. I want to consider all possible rectangles. But I'm saying that this rectangle and this rectangle have the same arrow. So if I'm looking for an ERM, a rectangle with minimum arrow, I could just as well only consider rectangles that rest on points from a sample. Now, a rectangle that rests on point of the sample rests on 2D many points. In every dimension, there is the 2 extreme points. So to consider all such rectangles, I can pick all possible ways of 2D tuples. For every such 2D tuple, figure out what the rectangle is, and then count how many arrows does my rectangle make, and I'll output the one with minimum arrow. So there are so many such tuples. And M is this number there. So I will get running time, which is going to be roughly this C times 2D plus ln 2 over delta divided by epsilon square. All this is my sample size to the power 2D. This is going to be my running time of a naive implementation of ERM. So you see, I describe my running time as a function of epsilon delta. I describe my running time as a function of epsilon and delta, and some extra parameter, which is D. So for any fixed D, this is polynomial. But if I allow D to be a variable, this is exponential. Right? So for any fixed D, I can learn rectangles in polynomial time. But if I want to learn rectangles and take into account D as a variable, then the algorithm that I have here is not polynomial time, because I have an exponent. I have D in the exponent. So the conclusion is that we have for every fixed dimension D, ERM over this class rectangles in RD can be implemented in time polynomial in 1 over epsilon and 1 over delta. And therefore, we have efficient learning. Because I know that ERM is a good learner, and I can implement it in polynomial time for fixed D. However, as a function of d, my runtime is exponential. The runtime of the algorithm that I gave you now. This algorithm that just searches over all possible rectangles. It's a very naive algorithm. So we can ask, can we do better? OK, so before I continue this discussion, are there any questions so far? Yes?
Can I just so first look at each dimension and use m squared steps to figure out the boundary of the rectangle on that dimension. Then I can just use d.
No. So maybe I didn't explain the algorithm well. So what the algorithm does, so let me explain my algorithm more clearly. I'm not trying to find extreme points in dimensions, because the points are labeled plus, minus, plus, minus. It's not realizable. It could be a big mixture of pluses and minuses. I don't have a notion of maximum point and minimum point, because I didn't assume that the data is realizable. It's a big mixture. So what does the algorithm do when it gets S? It kind of lists all 2D tuples from S. So you'll have T1, T2, up to T, S to the power 2D. Each Ti is a list of 2D points. Right? And now, H of Ti is the minimum rectangle that contains all members of Ti. So I give you a list of all 2D tuples, and whenever you got a D tuple, it doesn't matter how it looks. Here is a tuple. You search for the minimum axis-aligned rectangle that contains these points. And that will be your H of Ti. So you will go over all possible 2D tuples, and for each of them, you just try this rectangle. And now the next step is check the error with respect to S of each HTI, and output the one with minimum error, and output the minimizer. So the algorithm just lists all 2D tuples. Given a tuple, picks a rectangle, counts how many minuses inside, how many pluses outside. That's the error. Make such a long list. Go over the list, pick the one that made minimum error. And this will find you the ERM solution. OK, so we are out of time, so we will continue on Friday.